We're now going to look at a really important concept known as antiderivatives. So this is the idea kind of taking a derivative backwards. Or basically here, if capital F of x, so that's a capital F, if this is a function such that when you take its derivative you get little f of x, kind of a regular f of x, then what we say is that capital F of x is the antiderivative of f of x. Okay? So it's basically the antiderivative of a function is the function whose derivative is equal to the given function. Okay? So we got some little f of x here, and it wants us to find the antiderivative. And so there's really, at this point, no technique or anything here. We just got to think backwards. Okay? So the function 2x, can you think of a function that when I take its derivative I get 2x? And you might actually want to, if you want, you could pause the video and actually try these and see if you can find the antiderivatives. That might be good practice for you to get you thinking about it. So if you want to do that, then you can do that, and then you can resume the video, and we'll go ahead and find these antiderivatives. Okay, so let's see how you did. So this first one here, it's x squared, right? So because when you take the derivative, you bring down the 2, subtract 1 from the exponent, and you get 2x, right? And this one here, it's even easier to see, right? So clearly this was like an x cubed, and they brought the 3 down, subtracted 1 from the exponent, right? So, and these, these should be capital F of x, right? Capital F of x. These are the antiderivatives of these. So this is the function, you take its derivative, and you get that. So this one here, this is another power. Were you able to find this? So the answer is 1 over x. And the idea here is this is like x to the -1, and what you do is you bring down the -1, subtract 1, and you get -2. And so the negative comes from bringing down the -1, and then this square comes from when you subtract 1, you get -2, and that is x squared in the denominator, right? So this is the antiderivative to that. Okay? Similar here, the antiderivative to this is the square root of x, okay, or x to the 1/2, because you're basically bringing down the 1/2, and then you're subtracting 1 from the exponent, and you're getting a -1/2, which gives you the square root down here. So this 1/2 comes from bringing down the 1/2, and then you have the negative exponent, which brings that down. Okay, so you probably have done these maybe enough that you just recognize, oh yeah, that's what you get, and you just had to write it out and then give it a try, take the derivative and make sure you get that. Okay. Now these two are a little more tricky here, right? Because there's no actual power that I can take the derivative of and get x squared, right? So the idea here is, here's x squared, right? And it was a cubic function. But what I need is I need a 1/3 out front here, so that when I bring the 3 down, it cancels out and just gives you a 1, and I subtract 1 from the exponent, and I'm left with just the x squared instead of 3x squared, okay? So the 1/3, you got to add that constant multiple in order to cancel that out and leave you with just this. This is a similar idea. This is a lot like this one, right? So what I need here is I need a negative. It's the same as this, but I need a negative there so that when I bring the -1 down, they'll cancel out and it'll make this positive. Okay? And so so they can get a little bit tricky here. Okay? So all of these involve powers, and they can get a little tricky. So what we have here is we have a power rule. Okay, and this is going to be the first rule for antiderivatives, and then we're going to look at several more in the next chapter. And then if you take Calc 2, much of Calc 2 is how to find antiderivatives for functions that are a lot more complicated. So this is just the beginning of really important concepts in calculus. In fact, the derivative is one concept, and we're going to find out that the antiderivative is used to find the integral of a function, and we're going to learn about that in the next chapter. And so the integral is the other big concept, and we find that these are like inverse operations of one another. And this is where you can really see the inverse because we're doing it backwards, right? Now notice here, so what this says is the antiderivative to x of n, so this is a power function, is, and what you have here is x of n plus 1 over n plus 1 plus c. So it's kind of like this one here. I could have wrote this x cubed over 3. So this is the n plus 1, this is the n plus 1. And so this n plus 1 here basically is there so that when you bring down the n plus 1s, those can cancel out, and you subtract 1 from the exponent and you get this. Okay? And this plus c is there because, like we learned in the last video, that's how this is connected, is that for any one of these, there's actually a whole bunch of antiderivatives. So if this is an antiderivative, then so is, plus 17, or any number, any constant here. When I take the derivative of this, right, I'm going to bring down the 1/2, and then I get x to the negative 1/2, and then the constant just goes away. And so this is the 1 over 2 square root of x. So you actually have an infinite number of derivatives, but they all differ by a constant. So this is your plus c. Okay, so whenever you take an antiderivative, you've got to include a plus c. And we're going to see why that is in the next. So when you actually do applications, that plus c is important because we'll just see in the next video why it is. Okay, so now let's use this power rule to see how we can do some ones that are fairly complicated, but we can do them. Okay, so for this one here, f of x here is going to be, okay, the n is 3, so this will be x, and then 3 plus 1 is 4, over n plus 1, over 4, and then plus c. So now if you take this derivative, you bring down the 4s cancel out, subtract 1 from the exponent, and then the plus c, the c goes away, and you get x cubed. Okay? So let's try this one. Let's write this as an exponent, negative 1/2. Okay, so my power n is negative 1/2. So if I add 1 to that, I get a positive 1/2. So I can write this f of x, and this is equal to x to a positive 1/2 over a positive 1/2 plus c. Okay, so this is the n plus 1, and this is the n plus 1. So that 1/2 will get rid of this 1/2 when you bring it down, right? And then you subtract 1 from the exponent. Okay, so what I could do then is I could rewrite this as 2 square root of x plus c. Okay, so then you bring down the 1/2, and they'll cancel out. So what I did here, by the way, is I inverted the bottom, right, and multiplied. So the 1/2 would come down, cancel out, subtract 1, you'd get the negative exponent, right, and then the plus c would go away. Okay, so what about this one? Well, this would be x to the 2/3, right? So if I add 1 to this, that'd be 3/3, I'd get 5/3, right? So this would be x to the 5/3 over 5/3 plus c. And so usually you would write this as 3/5 x to the 5/3 plus c. Usually you invert that bottom. Okay, and you can, if it helps you just to do this, I mean, you could go right here. When I know that the n plus 1 is 5/3, I might just put the reciprocal of 5/3 in front and just write it like that. But oftentimes I will do this. It just helps me, and then I'll have a step where I simplify. Okay. Now the other thing here is you can use this with polynomials. So basically you can do this one term at a time. So the antiderivative, it's kind of like you can break up over a sum, you can pull out constant multiples, or you can just set aside the constant multiple for a minute, do the antiderivative to the power, and then put the constant multiple back, right? And same here with the sign in front of it, and same here. So basically what I could do here is I could do, just leave the 5 there, that's the constant multiple, do my rule here, x cubed and over 3. So this is n plus 1, n plus 1. And this would be minus 3, that's a constant multiple, then I would get x squared over 2. This is n plus 1, and that's the n plus 1 on bottom. And then this would just be x, right? You could just think of that as x. The derivative of x is 1, so that's the antiderivative. And then you would have a plus c. So then I could rewrite this like 5/3 x cubed minus 3/2 x squared plus x plus c. And that's how I would simplify it. Okay, so you can treat these kind of like you did derivatives, where you could pull out the constant multiple, use the power rule, put the constant multiple back, break it up over the sums and differences. You cannot break it up over a product, or I can't do like the antiderivative of the top and antiderivative of the bottom. You cannot do that. You can't break it up over products or quotients. Just like the derivative, you can't do that. There's going to be there's going to be special rules in Calc 2 where you're going to be able to undo those things, but certainly not at this point. Okay, so don't even worry about that. But this one, what I can do is I can rewrite this, right, as this would be like 3/2 x to the 1/2 plus 1/2 x to the negative 1/2. So I can rewrite it like this. So I'm taking this over that, and now I can use the power rule here, where I'd have 3/2. This would be x to the 3/2 over 3/2, like that, plus 1/2, and then this would be x to the, this would be 1/2 over 1/2. And this is using the power rules on those. And then look, this inverts, and you just get x to the 3/2. They cancel out, right? And then this would just be plus, and this would cancel out, and I would have x to the 1/2, right? And if I wanted to, and then I have a plus c. And if I wanted to, I could rewrite this as the square root of x cubed plus the square root of x plus c, or something like that. Okay? So this is just the beginning of another huge part of calculus, and in fact Calc 2 is kind of devoted to finding antiderivatives, and in some situations, it's not too bad. These are situations with powers and stuff that it's pretty easy, but they can get very, very difficult and very tricky. And it's also true that there's some functions that don't even have an antiderivative, at least as one of these elementary functions that we're used to. They might involve infinite polynomials or other things. So it can get very, very complicated. But at this point, this is the idea of an antiderivative and some basic rules to help you find some fairly simple antiderivatives. And you can see that there's quite a bit that you can do, even with this one rule, okay, along with the, breaking sums apart and pulling out constant multiples. You can do quite a bit just with this here. So this is a good start to this idea of antiderivatives. And so we're going to have one more video in this section where we'll actually use this to solve application problems involving falling bodies. And in fact, what we're going to do isn't very much different than what we've already done, except we're going to kind of formalize it with these rules, and you can kind of see how this is all related then to derivatives, antiderivatives, and stuff like that.